Nobody came to my DJ club yesterday. Feel so sad.
Nobody.
9 people, but nobody from this class. Huh? Pressure, it's peer pressure. Okay? Alright, y'all, so for today, I wrote it on the board, what we'll be doing. Happy Friday. We've got a lot to do today, probably.
Friday still have lesson at afternoon. No happy.
Afternoon, you will not be happy? I think you should be. It's the last stretch. Don't worry, all of March, there's no holidays, so very good. We'll do the questions, 9.3. So again, we did this yesterday, the whole simulation. If you want, I can still play around with it a little bit so that you can tell me what you want to see in order to solve these questions, okay? Otherwise, just keep your book open. Some of the English can really help you out, right? Where is, okay, 1, 2, 3 questions. 3 easy questions. 1, 2, and 3. 4. Here we go. Okay, so if there's any vocab we want to learn, just let me know. Right, so this is Q's 9.3 classwork. Okay. Any vocab that you need me to explain? Just let me know. Yes, pencil is better, guys. I hope everybody by now has a pencil. Especially when you're older, maybe AS levels, you should have a pencil for physics. The G10 people are driving me crazy. And I should also give you your graded classworks. All right, Hannah. Hey. Tina. You were always thinking Jack. So I think everybody did perfectly well. Olivia. Ilian. And Cynthia. So everybody's pretty much got this, but when you draw your molecules, you want to show some way of movement, right? So draw arrows, draw special little curves, whatever it takes to show that things are moving faster or slower, okay? That's pretty much it. So I'll give you guys 10 minutes on this one and let me know if you want me to switch anything up here. If there's any words you do not understand, I will write it on the board. And then once we're done, we'll start with a bit of temperature. is a freezer? Very cold fridge. I hope it's easy to understand. You have a refrigerator, and at the top, you have a cold part. So there's a freezer is like maybe -5 C, something like that. So based on what we did here with this experiment, you should be able to answer all of the questions. The old. Me? This? From school. There's a special room. Oh. Oh yeah, okay. I'll use a boring black one. Well, hopefully everybody knows what a freezer is. Maybe I'll use just blue. So freezer. Very cold box. I'll say it's a very cold box. But it's not going to lose gas, right? Look what we do here. Right, so if we have, guys, when you put the balloon in the freezer, this is the same thing that we did yesterday. This is freezing it. So because they slow down, yeah, like pressure, the pressure decreases. Yeah. So this is a bad example, this lab, but because the walls are fixed, right? Hold constant, yeah. Okay, but a balloon, the balloon's walls are not fixed. You can stretch them, bend them, things like that. Yellow. A little bit about energy. There's different kinds of energy. Water energy? I don't think so. But we do have thermal energy. Okay, still measured in joules, but that is still different from temperature. That's the whole point we are trying to say here, is that temperature is about the average kinetic energy of those little particles. Okay? So these little dots that we have is how fast they're moving. How fast they're moving, we can say it's in degrees, right? Degrees. So it's only in one location of an object. So don't think about the whole object, just touching one small part of it, okay?
Wait.
Wait, okay.
Okay, I just take it.
Wow, smart girl. You're the only one that thought of that.
I want the two. I can't understand. Right. Sorry.
Nothing to understand, right? This is total energy of all particles. This is just the energy of one piece of the object. So we're going to review that, right? Temperature is just average kinetic energy in one location. Girl, it's the same thing. Okay. Sometimes in a substance, not all of the molecules will have the same energy or move at the same speed. Okay? So when we say temperature, we're just taking the average energy that these individual atoms have. Okay? So on average, how much energy does each of these guys have? We're going to say higher. We're going to feel it. We can feel it's hot. Look at that. Right? So the temperature of the air over there is, that's how we feel the hotness. Right? So it's a measurement of the average kinetic energy. So we want to say temperature is kinetic energy. It's not just for gases, it's also for solids. Solids can feel hot. Liquids can also feel hot. Okay. And then if we have low kinetic energy, look at the motion of these particles. Quite relaxed. Girl, I'm not even finished with the slide yet. Then, okay. So the motion is very slow. Okay. If we have high kinetic energy, then we draw those same dots, and then they move very fast. So we want to draw the long lines, right? That's what I was looking for in the classwork. Okay. So low temperature means they're barely moving. High temperature, we touch it. That means they're moving around fast, jiggling around very fast. It's related to the speed of the particle. Yeah. We'll do a big comparison a little bit later. Okay. So again, in real life, we can feel something that's hot or it's cold. That's the difference, right? Do you know popcorn? You go to the movies, you make some popcorn. All those energies are still inside the seed. Yes, and you make it hot, it goes boom. And now those popcorn molecules are moving around very quickly. So next time you watch a movie and you eat some popcorn, you should think about physics. Okay?
It's stored, but it can be released to water for more energy.
Okay. Everybody agree? Who says the candle has more thermal energy? Tina? No? NK? Yeah, but with the candle, we're only looking at the candle, not the outside part. Who says the iceberg has more thermal energy? Rosalind? And Olivia? 2 people versus 1 person, and everybody else is... Okay. Maybe more, so 3 versus 1. Okay, well, our ice mountain or iceberg does indeed have more thermal energy, okay? Why is that? Because there's so many more atoms, there's so many more molecules, okay? If we talked about temperature, then maybe, yeah, the candle would have a higher temperature. So we want to think about the energy of all of the molecules.
What if the candle is bigger than the iceberg?
If you want to make a giant candle to prove Boomer wrong, you can do that. like we said last time, it has some energy. They're still moving around a little bit, so we want to give it some credit. Okay. Expansion, contraction. So again, just like gases, solids will also expand once they're heated up. So if we add some thermal energy, it'll make the particles move around faster. Okay? We already know that about gases, but what about solids? Well, if we take a fire to this solid metal, and we bring the fire close to it, it'll make it bigger.
Huh?
Yes.
热胀缩，热胀缩。
可是
Hot being cold snow.
just turn bigger.
Yeah. Some solids will not, okay? But most solids that are metal, maybe, they will expand a little bit, okay? So if we take away that same fire and cool it down, it's going to get smaller again.
可是它是 solid， 但是它物体它那个名字，它是元素，那个移动速度越快，就。
可是你拿滚那个弄它，可是你拿滚那个弄它不会化掉吗？
它不考虑化的情况，它只是管，就是好在可能还没到它的熔点。
All right. I hope you're explaining everything well in Chinese. What about a thermometer? Thermometer from back in the day, a long time ago, was the famous Italian scientist. 对. So they were very poor. They had no lab equipment. He had to make everything himself. It's pretty crazy. So yeah, he made the lens, right? He made the telescope. He's famous for that. He had to make that himself, just like cutting it with a knife. It's glass. So pretty crazy. But he also invented the first thermometer, and this is the original thermometer. I actually don't really understand what's going on here, but the lowest floating ball in the upper was the correct temperature, I guess. Okay? So they really tried to figure out, I mean, you're a human being from 500 years ago. You want to know, how can we measure how hot it is? Right? You would go outside and you say, oh, it's hot or it's cold. I don't know. Right? They want to measure things with numbers. We can count how many cows we have. Right? We can count how many apples are growing on the trees, but we want to count also temperature. Yeah. Scientists always want to put numbers on everything, right? Whether it's light, sound, heat, distances. Yeah.
How about the mercury thermometer?
Yeah, maybe that's I think the next one. Okay. Good question, Olivia. Here's the mercury thermometer. Yeah, they also found out that mercury expands a lot with changes in temperature. Okay. So because these materials expand when they're heated, they say, okay, well, when the mercury goes up, we can put numbers, right? Before they had no numbers. But they said, okay, let's put it in a very small tube, make it 1 mm diameter, and we can just mark it ourselves. We put the numbers ourselves, we decide now when my neighbor says it reaches this point, we both know it's the same temperature. So it's pretty simple how particles behave when they're heated and cooled, okay? Now, a long time ago, they just made up the numbers. They didn't really have a system, a really good system. It was whatever the king said, whatever the church said, but they really wanted something more logical, something that makes sense. And so people said we should base these on something more scientific. Okay, so we have 3 temperature scales today. That's the new one.
25 like this.
Well, that's how we measure them, sure. First one is Fahrenheit. You do not need to use this. It's stupid. It's American. Centigrade is middle. That's the one everybody uses
Yeah.
in real life. And this is the third secret one that
Secret.
is used with some physicists and also chemistry.
Chemistry.
Actually, it's mostly chemistry.
Kelvin.
Right.
What is Kelvin? Why
What is
doesn't
Kelvin?
it have the little circle?
It does not. I know. That's something strange about Kelvin is they don't put the degrees.
一个是
Okay. But you can still say degrees Kelvin. It's fine. We don't care about F. Centigrade is used for the whole rest of the world and is by regular scientists. So normal scientist measuring like geology or something, they'll use centigrade because it makes sense. Kelvin is a special one that's just used by a few scientists that are involved in thermal stuff, thermal chemistry, or thermal physics.
thermal. It means a little.
Thermal.
Thermal. What means?
Thermal means hotness.
Oh.
Right? This chapter is thermal physics.
Oh.
So
Bigger. Yeah.
Kelvin is usually a big number. We will see very soon. Okay. Just real quick, we have the different values for the same thing. So this is the conversion. Okay. Kelvin is just the name of a guy, right?
Oh.
Let's see, centigrade. This is our main one. We like this one.
Yeah.
What's the meaning of this? Why is it special? Can anybody tell me?
The other two was based on this one.
No.
It has points. Maybe point like
Oh.
37.1.
Well, every temperature scale has a point.
Oh.
37. You can have 37 Fahrenheit, centigrade, Kelvin. What's
It starts with 0.
so from here
Yeah.
and
Oh, 100. It's like the
then
water
the
matter.
K don't have a negative.
oh my gosh, too smart. Wait, just talk about centigrade first, okay? So the reason that centigrade is special is because they use the boiling and melting point of water. Wait, sorry. Melting point, freezing point is the same thing. So they said we've got liquid water. We want to say when does it boil? When does it freeze? We'll put that at 100 and 0. Okay. Then we've got something called absolute zero. Whoops. Okay. Your book does talk about Kelvin a little bit. Okay. And as Tina has observed, there's no way for it to be negative. Look at that. Fahrenheit is negative 460. Centigrade is negative 273. But Kelvin is special because it's always positive. And that makes calculations for scientists very easy. Yeah. Okay. Again, in this class, we're still babies. We're not going to give crazy equations. But just know that when we put these into our tools, if something becomes negative, that can be a big problem and messes things up. Okay. So how to view temperature, right? That's 0. The oldest style, right? Changing the shape of an object, that's the mercury. Okay. And this is basically how they did it, 300 years ago. They just tested out. Let's mark it as a grade, right? So using the grade system, that's those little lines. So whenever you see the word grade, you should think about these little lines. Okay. Same thing with a ruler. Same thing. Let's see, right? So this was their process. These really smart scientists in Europe. They said, well, we're going to figure out when does water become ice? When does water start to boil? And we just put that as 0 and put that as 100. And then everything in between, just mark it as 0 through 100. Okay. Humans have 10 fingers, so that's why we really like using tens and hundreds. Things like that. Okay. I think that's about it, right? So the book does say stuff about Kelvin, right? Let's see. 9.3. Gas levels. Kelvin temperatures. Okay, yeah. So they talk about on page 163. Okay. Which book? Your English book. All right, so we've got 3 thermometers: centigrade, Fahrenheit, Kelvin. Okay. If we want our TK, this should be TK. Temperature Kelvin. Right. So. What? Okay. All right, very basic formula for converting from centigrade to Kelvin. Okay. That's why we said here, the centigrade system has one problem, is it can be negative. We don't like that, right? So we figured out a way to make temperature to never be negative, so that their equations would work correctly, as I said earlier. Okay? So they found out what is absolute zero. What's the coldest the universe can ever get, right? We could just add up from there. That's it. So they found that the coldest possible temperature in nature or in the lab is negative 273. They did this in the laboratory. And everything stops, right? If it's absolute zero, you put your finger inside, your finger is dead.
Oh no!
Yes, very scary.
I want to know why we make 273.15.
Because in centigrade, they found out that that's the coldest we can get.
Oh.
That's the coldest anything can get is that,
Oh.
right? So if we set that equal to 0, that's our Kelvin, 0 Kelvin.
0.
Yeah. And then plus 273 will bring us up to centigrade if we want. Right? So that's why, yeah. So Kelvin, the absolute coldest it can be, in Kelvin that's 0. That makes sense. What's the coldest anything can get is 0. And then anything a little bit higher will be, get toasty. Okay? So that's why your body temperature is 37 degrees centigrade, right? But if you change that to Kelvin, suddenly your body temperature is 310.
Oh.
Yeah, in Kelvin.
Wow, Dad.
Okay? So if you get into chemistry, you get into thermal physics, you have to get used to the idea that your temperature is going to be very big. You'll have big numbers. Okay? So these are some examples of Kelvin scale. We have to finish class very soon. Okay? These are some examples of Kelvin scale. Lowest temperature we can ever get is 0.000001 Kelvin. And then they talk about some stuff that happens on Earth. Then they start talking about some stuff that happens in space. Okay. And that's it. Japan. Solar corona. Coronavirus.
Huh?
No, I'm joking. It's around the sun. At the edge. It's at the edge of the sun. Yeah. Guys, wrap up that classwork. It should not be hard. I will put the answers in Teams very soon. 谢谢。
再见，拜拜。
拜拜，enjoy your class。
就是体育的，就是。Mr. Hill, how can I calculate the how often the air will
Bye. Enjoy your weekend.
heat
Don't forget to like and subscribe.
into the walls of the can?